Hello physical science students, and welcome to another Hook video brought to you by Coleman, Langham, and Litz. Our Hook videos are meant to spark your interest in our upcoming topics. And our next topic we're going to be working on is waves. So sit back, relax, and enjoy the videos.
In Voice Flame Extinguisher, Adam and Jamie investigated the viability of fighting fires with sound waves. But what we didn't have time to show you was when they explored another fire phenomenon, the Rubens tube.
This is a stunning visual representation of a sound wave.
Yeah, let's fire it up and see what it does.
All right.
It's a classic physics experiment that has recently become an internet phenomenon. A length of pipe is perforated along the top and sealed at both ends. One seal is attached to a small speaker, the other to a supply of a flammable gas. The pipe is filled with the gas, and the gas leaking from the perforations is lit.
Oh, it's beautiful.
So this is called a Rubens tube, right?
Yep, it's Rubens tube all right, and what you're seeing is a standing wave rendered in fire. This is how it works. When the guys play a tone through the speaker, the sound wave enters the tube, and the confined space creates reflections and interference, which combine to create a standing wave. The standing wave affects the air pressure inside the tube, which affects the amount of gas coming out of each perforation, which affects the size of each individual flame.
And what we're looking at is areas of higher and lower compression being made by the sound waves down the tube, affecting how much gas comes out of each hole.
If you keep the frequency constant, you can determine the wavelength by simply measuring it with a ruler. And if you think it looks familiar, it probably is. Rubens tubes have been around since 1905, when Heinrich Rubin fired up the first.
Look at that. Yeah, we're watching the waves pile up. Yeah, totally.
It worked.
That is very, very, very cool. I had not imagined that there was such a clear visual representation of a sound wave.
Alright, so our next video is a very similar concept, except this one involving a plate and some salt. So those are some examples involving interactions between sound waves. Now here's an example of an interaction between electrons.
You'd expect that if I roll a few of these balls down the lane, they'll either be stopped by the barrier or pass through one or the other slit and hit the screen at the back. And in fact, that's just what happens. Those balls that make it through always hit the screen directly behind either the left slit or the right slit. The double slit experiment was much like this, except instead of bowling balls, you use electrons, which are billions of times smaller. You can picture them like this. Let's see what happens if I throw a bunch of these balls. When electrons are hurled at the two slits, something very different happens on the other side. Instead of hitting just two areas, the electrons land all over the detector screen, creating a pattern of stripes, including some right between the two slits, the very place you'd think would be blocked. So, what's going on? Well, to physicists, even in the 1920s, this pattern could mean only one thing: waves. Waves do all kinds of interesting things, things that bowling balls would never do. They can split. They can combine. If I sent a wave of water through the double slits, it would split in two, and then the two sets of waves would intersect. Their peaks and valleys would combine, getting bigger in some places, smaller in others, and sometimes they'd cancel each other out. With the height of the water corresponding to brightness on the screen, the peaks and valleys would create a series of stripes and what's known as an interference pattern. So, how could electrons, which are particles, form that pattern? How could a single electron end up in places a wave would go?
So this might be a topic, along with the others, that you wish to explore more about in our future unit. Our last video is an example of some engineering students at George Mason University using their knowledge of physics to create something that could better society.
We're both graduating from the Electrical and Computer Engineering department at George Mason University this coming May. We're just going to test out our device that we use that uses sound frequencies to extinguish flames.
I see this device being applied to a lot of things. First off, I think in the kitchen, it could be on top of a stovetop. But eventually, I'd like to see this applied to maybe swarm robotics, where it'd be attached to a drone, and that would be applied to forest fires or even building fires, where you wouldn't want to sacrifice human life.
Professor Brian Mark really stepped in to help us.
He just gave us a lot of support.
I think as a whole, engineering is really just finding solutions finding simple solutions to complicated problems. Engineering is all about finding a way to make the impossible possible. So that's what we do.
And that concludes our hook video. I would like to wish you luck on your journey through our next unit, Waves.